Thanks. So first of all, I'd like to thank the organizers for the kind invitation. So it's a really great pleasure. I always enjoy Paris. So I visit Paris many times with Michael, ENS many times too. And so it's once again coming back. It's a really great pleasure. So this is a joint work with Tian Ma, and so let's see which one is the pointer. Yeah, Tian Ma, we share same advisor, and he in our same period of time in Nanzhou University in northwest part of China near Gobi Desert. It's a beautiful place and a nice place to visit. Anyway, so we have been collaborating for many years, and since 1996, and so at the time I finished my PhD in Nanzhou, I went to Indiana working with Roger Terman and Jack Louis Lyons, and wrote a number of papers on primitive equations. Later on, we moved on to this the geometric theory of incompressible flows and then phase transitions. So this is one of the things. But last 10 years, I spent most of my time on theoretical physics. So I'll report some of the issues and related to GFD, okay? And I try, the purpose is try to understand some basic issues from first principles. And this is we have been trying. And okay, so let me put things in perspective, in a bigger perspective, so that so we wrote a book, and we studied the theoretical physics around 2009. And so the whole purpose is try to derive, following Einstein and Dirac and those giants, to derive physical laws from first principles. And also we believe, of course it's not we believe, Einstein, people believed, the laws should be simple and has its beauty. And the simplicity is not meant to be stability, is related to stability. The universe existing here, there should be a certain stability. Without a stability, there will be no existence. So the simplicity in Chinese, like Lao Tzu, for instance, Confucius, for instance, the doctrine of mean, for instance, which is really related to stability. So it's a really important issue. So without any modeling or physical quantity, laws should be expressed in simplicity and beauty. And this is one of the things we want to follow. And second thing, the second general principle, in fact, of course, the laws should be, for each physical system, the laws should be written down in mathematical equations. And I don't want to go to the philosophical argument of this, but the most important issue here is that each physical system would have certain symmetry. The symmetry gives you a certain type of functional, which is a certain form of energy. So basically, you have symmetry. The symmetry dictates the certain type of energy, and the energy, certain variational form of energy, would give you a physical law. And so far, and we found no exception. Okay, so there are two types of laws. One is motion dynamics. The other one is interactions. Interactions give you forces. And so all these two categories of laws are of this type. So basically, you want to find some certain energy through certain symmetry of the system. And once you get the symmetry, and then you get F, and then like Einstein-Hilbert action, for instance, for gravity. It's simply like integration of the scalar curvature. And for weak and strong interactions, it would get like Yang-Mills action. And now also for dynamical laws, you simply have those type of energies. So this is the general principle I want to talk about, the modeling, so the issue. So basically, you want to study physics. You start with symmetry, and then you derive the energy, and then you derive the law. So this is very simple, elegant, I think. So once again, I emphasize, for instance, for interactions, you would have those symmetries, and those symmetries gives you in a unique fashion the actions. And then you take certain variational principle, and then you derive the laws. So this is for interactions. And here in this room, I think the audience would like for dynamical laws for motions. In fact, a couple of years ago, we wrote a paper which says that all motion dynamics can be, so you can find some kind of energy for each motion dynamical system, And this system, this energy is subject to certain symmetry, like especially the rotational symmetry. And the rotational symmetry would give you this essentially the energy, and then you take a proper variation. You would get some kind of law of this nature, dynamical law. And this, I put a delta L here, which means L represents certain constraint. Okay, so they're like Navier-Stokes. Okay, so all dynamical law can be written in such a format. And let me give you a simple example. Okay, can I do it here? Okay, so this it does work. So also in some cases, you may have a physical system coupling different subsystems. So one of the things is that you have, if you have one bigger system coupling several systems, and then each subsystem has its own symmetry, and its own symmetry would give you its own energy. And then the coupling for the bigger system is simply addition, the summation of the energy of the small part, the subsystems. So this coupling is done through adding the energy up. Once your energy added up, then you take a variational principle, you get a law. But in this situation, there's a symmetry breaking term. The BU represents the symmetry breaking because you have several symmetries. And then when you write down the law for the global system, then some of the symmetries will break. So this is also a general principle. Right, so let me, of course, if your system is in a certain equilibrium, so you drop the time component, and you have this equilibrium system. Okay, so this is the general strategy. So let me give you a simple example. Okay, this is Bosniak equation. We all know this, right? In this room, so we have this three-dimensional velocity. We have temperature equation, and we're assuming this is incompressible. And so in this situation, you have all those quantities. I think everybody in this room understands this quantities. So in this situation, you write down the energy, this functional F, which is simply the kinetic energy and also the energy due to temperature change, right? So this is right, and this is a very simple energy. And then the way you derive this equation can be, this equation, system equations can really be derived from this D is the total derivative, taking variation subject to divergence-free condition. And a divergence-free condition gives you a gradient pressure. So everything comes. Okay, but then you also have this B term because you are coupling two processes. One is like velocity, the other one is temperature, which has different type of symmetries. And then you have a term which is given here. So in other words, so this is a simple demonstration of this general principle, so that all physical motion dynamical laws is a variation, is like a negative gradient of some kind of variation of certain energy of the system. Okay, so in the paper, we have all sorts of examples, and you see that it's quite simple. It's not hard to read it. Okay, so this is just like a general introduction about modeling. So that we are talking about, because people in this room are very interested in modeling the physical processes, and so I try to put this in this perspective as from first principles. Now suppose you have this type of dynamical law. Okay, I want to study phase transitions, so I'm interested in the dissipative systems. Okay, so most dissipative systems. So what you do is that thinking about like Bosniak, for instance. So here the U here can stand for like velocity and the temperature. You put things together in one state variable U, and I'm interested in the transition from one basic state, which is you call U0, and then this U here stands for a deviation. Okay, so if you have a basic state, U bar, let's say, and then your U is U prime plus U bar. So here, this is U. So you write down equation for U prime. You suppress the prime. So then you get system equations of this nature. This is a dissipative system. And then you would have a linear part. You also have a nonlinear part, and then time derivative part. Navier-Stokes and Bosniak, all those can be written in such a fashion. Okay. So this is a general form. So now the phase transition in a general sense is you want to study the transition from one particular state, say for instance from U bar to new states. Okay, so this is phase transition problem. Okay, And so, of course, this is closely related to bifurcation and even tipping points. Michael was talking about it. Here, one of the differences I'm talking about here is I'm talking about deterministic system here, okay? And this bifurcation theory has been around for doing this thing. And classically, when you do bifurcation, what you do is that you start from this basic state, and you look for new solutions. Once you get a new solution, you look for stability of the new solutions. By taking linearization around the new states, then you study the linear spectrum of the linearization around the new solution. And this can be very, very complicated. And also, there are situations where you have a lot of transient states, especially in climate. For instance, Michael mentioned von Neumann's early paper saying that there are three classes of problems. One, you have a forecast with short-term, long-term, and the intermediate terms. And, but in the intermediate terms, there are a lot of transient states. And if you're simply talking about a new state and talk about stability, you may miss the transient states. And also, you may get states which are not stable. So from bifurcation point of view. So what we did was, the starting point for this entire theory was to look for all possible transition states, physical states. Instead of looking for one particular bifurcation state, then you do linearization, stability. That's extremely hard. And also you miss things. And then what we did was say, okay, let's look for all possible transition states at once. And it turns out that mathematically it's much simpler than the bifurcation problem and the stability problem. So it's much easier. So this is the how the whole theory got started. And so what we do is that, let's say, you start from the linear instability. So basically, it's like you look at the eigenvalues of a linear operator. And so which basically you want to solve, look at that, this L lambda W equals to beta lambda W here. So that this is for each lambda is a control parameter controlling the system, like Reynolds number, all those things. And for each lambda fixed, you can solve this eigenvalue problem. So that you have a sequence of eigenvalues, betas. But for different lambdas, this lambda changes, those betas changing, right? Changes. And the linear instability says that when lambda crosses certain threshold, lambda 0, and the beta, those betas in the beginning will stay in the left-hand side complex plane, and some of them will cross as lambda crosses lambda 0, right? So then you get a linear instability. So basically, this is linear instability. Let's see, not working well. So this is linear instability. And we proved the theorem, which says that whenever you have linear instability for dissipative systems, you always have a phase transition, dynamical phase transition. Always. So dynamic phase transition always happen. This is for nonlinear system. So linear instability implies the nonlinear phase transition for the system. And then the question is that what is the type? When you want to see more details about the phase transitions. So the type of phase transitions will be dictated by nonlinear interactions of different modes. So basically that's that. So then we want to say, so what we do then is that we reduce things to like Honghu did beautiful about the central manifold reduction. We can use central manifold reduction to reduce things to the central manifold, and which captures all the nonlinear interactions. And then you will be able to say precisely all possible transitions and the type of transition you have. So this is the entire philosophy of doing that. And this whole thing has developed in the early 2000, and we wrote a book which published it by Springer in 2013. And last year we were asked for the second edition. So second edition, I'm only in the stage of doing Galilei proof. So it should come out in next month, okay? So early stage, they have like 500 some pages, now got 800 some pages. The reason is the addition of statistical physics and the topological phase transition to the new book, okay? So one of the things we derive from this theory is that you can derive a general principle. So the phase transitions, I should say deterministic dissipative systems can be classified into three categories. One is called continuous, meaning that the transition states all stay in the neighborhood of the basic state. This is one category. The second situation is we call this catastrophic, which basically says that whenever lambda crosses, the transition goes to far field. And so this is the second category. And the third category is that it jumps between things in the neighborhood or things in the far field. So we call this third type of transition, which we call random transition. The reason we call it random is due to fluctuations. Your fluctuation takes you to different regimes. So this is the type you would get. And so there's a lot of examples of this in the book we just mentioned. And once again, the technical ingredients of this is through central manifold reduction, and give you you have a full classification of all type of flows structures. So then you get all this thing come out. So it's very natural. And the theory is not hard to apply to different systems. And so once again, we have applied to this to all range of problems. And in fact, this principle, for instance, the general principle can be derived from this theory, and no bifurcation theory would give you such a thing, because you are really capturing all possible transitions. This is the goal. Okay. Let me say something about one application to statistical physics, but because phase transition starts from statistical physics, and so if you look at thermodynamical systems, one of the things during this day, when I was a student, we really like physics. So then we try to understand statistical physics, thermodynamics. It wasn't so easy. And later on, in the last couple of years, we realized that there's more basic things in statistical physics. Here's what you do. So you have first law, second laws, other things in statistical physics. But in fact, if you look at the classical books on statistical mechanics, people would say you can derive from second law that the potential would be decreasing. But if you look carefully, all the derivations, which has a hidden assumption saying that this potential is decreasing, because a lot of proofs are having implicit function theorems mixed up, so that there are so many quantities. So then we said, okay, why not? So later on, when we wrote the paper, we discovered a YouTube video by Richard Feynman. And the video title is called Entropy. There are two parts. Basically, Feynman, we said, okay, second law is more or less equivalent to thermodynamic potential being decreasing. And anyway, what we did was, we start from this thermodynamic potential. So each thermodynamic system, you would have a control parameter, you have order parameters, and then you have a potential. This goes back to our general guiding principle in the very beginning. This potential function is energy, it's proper energy. It's also called free energy in different settings. And then this potential would be, if you start from a line equilibrium state, and then this potential will be decreasing along the trajectories. So this is like then if at the end it settles down to equilibrium. So this is we call this as a potential descending principle. Then if you start from this, you can really derive everything from statistical mechanics, physics. So let's look at how we do this. So in a simple fashion. So this thing evolved, so the potential dependent principle would give you the first law, for instance. Suppose you are in the equilibrium. First law is about equilibrium, right? And then you take the total derivative of this f into this variable, so you get this term. This is simply like a total differential. Then this term, because at the equilibrium, this is 0, so you get that this equals to that. That is first law, exactly first law. Okay? What is the second law? The second law says that you still take the total derivatives, but second law starts from line equilibrium state. If you have a line equilibrium state, and then the potential would be decreasing. Well, this potential would decrease in thinking about the time, you're advancing time in a positive fashion, so this term will be negative. Now this is negative, same channel, this channel would give you this thing equal to that, but this is less than 0, so the whole thing is less than this guy. That's the second law. So it gives you the second law. Okay. And also gives you like all the statistics. Suppose you are at equilibrium. Suppose you are at equilibrium. In fact, you have this Maxwell-Boltzmann distribution, Bose-Einstein distribution, Fermi-Dirac distribution. Those are for different particle systems. For instance, for like classical system, you get this MB distribution, or for Fermi systems, you get Fermi-Dirac, you get these distributions. And there's a beautiful book written by Schrödinger, for instance, and which derives those distributions by using the maximum entropy. That's one entropy ratio. Entropy is what? Entropy is K log W. This is entropy. It's K log W. W is the total number of multiple states of the system. And then when entropy is largest, meaning that this takes the largest probability. And then you can derive this, those things very easy. But this is really talking about the distribution of the equilibrium. But equilibrium doesn't have to be at the maximum entropy. So then what we do is instead, so you write down, basically the question is that you have different energy levels of particles. You want to find this distribution quantity. So subject to those constraints, there's an energy constraint and total number of particle constraint. And then what you do is that you write down this type of energy, free energy, and then you take variation from the free energy. The free energy is at equilibrium. So the derivative will be 0. Then take W to be different quantities depending on the system, you write down equation right away. So you have those distributions. So this is how you derive those distributions, so in a very simple fashion. Okay. So the next issue, it gives you this descending principle also gives you irreversibility, a way to characterize irreversibility. Normally, this is done through entropy being increasing. This is people always talk about entropy being increasing is a law for describing irreversibility. But what happens is that this like a potential being decreasing at some non-equilibrium state really gives you exactly the irreversibility. The argument here is that when you talk about the physical quantity, you have three type of quantities here. One is auto parameters, which is like state variables, like U. One group is called control parameters. Those are lambdas, okay? And then there's also the energy. Energy is a higher level quantity. So the energy being decreasing is a better quantity for describing irreversibility. That's what we're arguing, okay? Because this is like decreasing, so it can never come back. So that's exactly it. And the other thing is that it gives you a dynamical law. So that's something we want. You want a slight phase transition, you need a dynamical law. So basically the dynamical law is, this is the free energy of the thermodynamical energy. You take proper variation, you get this dynamical law. And this dynamical law, so this gives you nonlinear, this gives you the transformation from non-equilibrium state to equilibrium state. So that you study, so basically using this law, you can study the phase transition behavior of the thermodynamical systems. So this is something about general about statistical physics. Let me go back to phase transition. Okay, we have the law now. Okay, from those two principles, we derive all these related things. The first law, second law, distributions, stuff like that, for the statistical system. But now we also have the law. Once we have the law, we have equation, right? Once we have equation, we can study. And the equation, all you need is a certain symmetry plus the physical picture, and then you derive the energy. And once you have energy, you derive the law, right? And then we do the transition, phase transition. So this is now. So then after a few years of work, we have proved the following thing, because there's also a classification. We did a classification, we call it dynamical classification. There are three categories, three types: continuous, catastrophic, and random, right? That's our new classification. But classically, for thermodynamical systems, there's also Ehrenfest classification, which basically you calculate how many derivatives you can take at a critical threshold of the free energy. And so whenever you get jump, so you got nth. So the nth derivative has a jump, then you got nth order phase transition. And then here's what we proved. This side is an phase type of phase transition classification. And on this side, we have classification in dynamic classification. So here it's more theoretical in a sense that I can write down the energy, I can tell you which type of the transition you would have. And this is in a sense more like a experimental. You can do experiments to calculate, to check the type of transition you would get. For instance, for gas-liquid phase transition, for instance, for gas-liquid phase transition, you have T here, you have pressure. So this is like a liquid. This is a gas. So if you go across this line, you get first order transition. So this is like a first order. So there's a critical point here. You can get like this is like a second order. And in fact, you can go beyond this, you get third order. So this is the current picture of a gas-liquid phase transition. And so basically, if you want to say, okay, in a classical fashion, you can do a lot of experiments. Those temperature and P here are control parameters. You can take a pressure and the temperature here, you do experiment, right? And you can do a lot of experiments. You can plot this phase transition dynamic curve, this curve here. And but once you get into the range like here, it's hard because you need to check higher order derivatives. Experimentally, it's hard to do higher order derivatives. It's like Navier-Stokes. 3D Navier-Stokes, one of the millennium problem is to find singularities of possible blowups of 3D Navier-Stokes. But people like Tom Ho in Caltech, they want to do this numerically. It's a difficult task because it's singularities. It's hard to catch numerically. But anyway, so what we're saying is that the phase diagram here can be plotted easy by write down proper energy and doing the phase transition dynamics as we do. And you can write down those things quickly and then see all the phase transitions right away. So this is the advantage. So one more thing I want to emphasize here is that according to this classical definition, you would have arbitrary order, first order, second order, and third order, things like that. But in fact, what we are proving here, you only have first, second, and third order, no more higher orders, and physically. So this is the theorem we proved. And let me give you some details how this thing. So for instance, let's look at a situation. You have a homogeneous system. In that situation, the free energy doesn't have any Laplacian things like calculating. So then taking the deviation from the basic flow, basic state, you would have a f of this type. You can have alpha, beta. You have alpha and B0, B1. And depending on different situations, so for instance, in this situation, where B0 is 0, so you don't have this term, and you have alpha and B1, then you get, if B1 is less than 0, you would get a pitchfork bifurcation. But this is, you have to understand this is a transition, and of course, this is just like a demonstrating. So the pitchfork bifurcation will give something like this. Then you put this thing back to the energy, see what you get. So in this setting, you put that thing in the back to the energy, your energy functional will be of this type. So you just put back a solution inside. And then take derivatives of this free energy with respect to lambda, which is control parameter. You can compute the first derivative, second derivative, you get a jump from 0 to here. Then this is a second order transition, you see right away. Okay? So something of this nature. And you can do like other type of transitions. But in particular, you don't have higher than 3 order of phase transition because in that situation, your energy has to be of this type. But in nature, you don't have these fractions like causing certain singularities. So that's not possible. Okay, so now let's say something about Jeff. How much time I have? 15?
Well, we should give 5 minutes for a question.
Okay. So it should be okay. So the one of the applications for the phase transition dynamics are the ones using applied to like fluid mechanics, the class or GFD problems, and we worked on all those examples. We did like classical problems like binary convection, Taylor problem, all those things. And also we apply to GFD problems, including the ones like Mergani flow with Hank Dijkstra. He's not here, but this is my former student who is a professor in Turkey right now. And I did a number of things on GFD. And we also did the kinematic instability and the phase transitions associated with this. This paper was done with Ming Kai in Florida State. He did some of these things in early stage. He's a meteorologist. And okay, anyway. And you can also do this on 3D continuously stratified rotating Bosniak equations. And lately, and the strategies, you can also apply this computational strategy to compute the eigenfunctions. And Honghu presented one of the most important techniques, as I said, is related to central manifold reduction. The backward-forward approach Honghu just presented gives you a very beautiful way for doing things computationally also. And anyway, so I don't think I have much time. Maybe I should skip the kinematic instability result, and instead I say a little bit about topological phase transition, because this is something which I think Michael mentioned slightly a little bit, but it's a very important concept related to quantum phase transition for like condensates, quantum condensates, and also for boundary layer separation. Even for tropical cyclones and those type of things, all can be classified as a type of transition we call topological phase transition. Okay, basic idea is that you have two types. Basically, you have dynamical transition, which gives you all the transitions of solutions of PDEs models. And the topological transition basically says that if you have this thing, you solving the PDE model, then you look at the structure in a physical space, how the topological structure changes in the physical space. Then the topological change of this flow or the solution in the physical space gives you the topological phase transition. So there are two layers. One layer is you have to solve PDE. Then you look at the picture, how the picture changes. So that this is like this is much more difficult than the dynamical transition, because you have to understand dynamical transition first. Then you have to connect this to the topological pattern of the solutions. So this is in quantum, lot of like studies in quantum phase transitions which are of the similar types, but even the definition is not so clear. So basically, what we do is that we say, okay, for fluids, this is very clear. In fact, for quantum condensates, this is also can be made very precise. Anyway, so now we wrote a sequence of papers, and the starting point and the early things, we did some geometric theory for incompressible flows, which is relevant. And for quantum phase transitions, which is associated with the mechanism of shape conductivity of quantum condensates, which are related to the first two papers here. But what I really want to talk about is something here, and also related wholly work with Michael we did. Okay. So the idea of doing this is very simple. At the end, everything, if you understand the things, basic intrinsic detail, the properties of the system, the things becomes very simple. So here in the situation, you have two stages. One stage is suppose you have a velocity field now, right? Now, suppose you have a velocity field. I want to see the possible transition at a proper time t naught. And I do Taylor expansion at time and they get a leading order and first order. I'm also interested in the normal derivative of the velocity field. Okay, so you have Taylor expansion of those things. And then you can formulate a kinematic condition, necessary sufficient conditions for this flow having some kind of separation. So basically, the first one is the Prandtl condition. It's the V, the normal derivative of velocity field is 0 for the leading order. This is really the Prandtl condition, which means the vorticity is 0. I'm talking about 2D now. Then this index is different minus half, which says that the singular point has to be non-degenerate, because if it's it has to be degenerate. If it's non-degenerate, then it's stable and doesn't have the transition. And then those things are just local analyticity. The analyticity, it means the flow is not so bad. Then you have the following theorem. The following theorem basically says that whenever this condition is satisfied, then you always have a structural bifurcation. This structural bifurcation is a topological bifurcation, transition or something like that. And of course, this here I didn't link to PD Navier-Stokes. It's just to say I have this velocity field depending on a parameter time. And having those conditions satisfied, basically the Prandtl condition plus the degeneracy of the singular point. Then you have this phase transition, topological transition. So in the case where this index is 0, you get shear flow and undergoes a degenerate singular point, you get a vortex forming. So that's the result. And now you try to link to the PD. Linking to PD is very difficult because the previous theorem is basically kinematic. But how do you link to the PD solution? Because topological phase transition is really, you want to understand the topological change of the solutions of the PD, right? So now you go back to PD. So now suppose like you work on this Navier-Stokes, right? For this Navier-Stokes, we derived a condition. If basically what it says, this is the initial data. You take a normal derivative, in the normal on the boundary. So that here K is the curvature of the boundary, and this is forcing. So K is curvature. This is tau is the tangential component of the forcing. So basically, this condition, if you set the left-hand side to be 0, if this is which is the vorticity vanishes. If you set this to be 0, then you solve this equation. The right-hand side solve the t here, and also the time and the location. You solve this equation for the time and the location with the left-hand side to be 0. You get the suppression point. So in other words, this equation does link the suppression point to the PD. Okay, so this is so linking the kinematic theory we proved it with Michael to Navier-Stokes in this type. In fact, this is for like non-zero boundary conditions, but with zero boundary with like a free slip boundary condition, you can also derive similar things. In this situation, you set left-hand side equal to 0. You get an equation which gives you the time and the location where the suppression occurs. So this gives you some characterization. In fact, you can apply this to like a subpologile of the Atlantic Ocean, which is related to curvature and things like that. And I don't think I have time to talk more about this. Let me make a summary of this. So basically, we have attempted to derive models through like a simple, from symmetry, derive the unique energy. So in other words, the energy is unique. People are fussing up, but in the physics community, people say, okay, if this model doesn't fit the physics, then they want to change the model. How do they change the model? They change the action. They change the action arbitrarily, putting a lot of things in there. But you lose basic principles. But you cannot change the actions. Like Einstein, if you read the book, there was a beautiful book written by Pels about Einstein called the Statistical Law. It's a beautiful book, which basically Einstein many times think his theory cannot be changed. The reason his theory, I think that what he meant is that the action is unique, it's some certain type of energy. You cannot change the energy of a system. And so this is, in this sense, energy is unique. And then what we added up to this is that when you derive the equation from the energy, you take a subject to energy momentum conservation law, which is the constraint, which gives you things like pressure, which captures a lot of essential details which are missing in the physical models. The second thing we did here, we did this dynamical transition theory, and also we have showing that statistical physics can really be built upon some two simple principles. And with these two principles, you have much easier to understand. I taught a course on statistical physics through these two principles. And students got much better understanding on the subject, I believe. And then we also say there's the topological phase transition, which can be applied to various things like sunspots, also like why you have a spiral structure of a galaxy, things like that. All topological structure change, or it can be classified as a topological phase transition problems. Of course, the boundary layer separation, also the formation of cyclones, tropical cyclones, those type of things also are topological problems. Okay, so you have PD, but then you want to see the formation of a tropical cyclone. It is a topological phase transition problem. So those are very important, right? But there are many things still open, especially for topological phase transition, because there are two stages. The linking of the topological structure of the solutions to PDE is extremely hard. And so I invite everybody to work on this field. Thank you.
Thank you. Quite an inspirational talk.
Thanks.
Questions?
Yeah.
So about the last topic that you mentioned on boundary layer separation, so you derive a criterion for a boundary layer separation, right?
Yes,
or
yes.
a characterization of the separation point. Are you able to exhibit solutions that actually satisfy this criterion? And do you know what they look like close to the separation point?
Yeah, I think I do. Hold on 1 second, let's see. I may have a slide somewhere. Yes.
Okay.
Okay. I think I may have some pictures here. Let me check if I do. Do I? No, I don't. So yes, it's basically, some years ago, I had a postdoc, Chen Wang and Jianguo Liu's former student. He was a postdoc in Indiana. So he did like a driven cavity flow. The flow is driven by the boundary conditions on the top. And he was able to demonstrate, it's not hard computation, you compute the flow and you compute the vorticity. Basically the condition I was mentioning, 4 conditions, is equivalent to this like something called the vorticity crisis. So in other words, the conditions, so vorticity can be something like this. So this is like the vorticity, and but what happens is that this is the tau. So but when vorticity touches, so basically vorticity touches the axis, is the condition. So when vorticity was like that, was below the axis, then it touches and then goes beyond. So that whenever it touches, the flow starts forming. So basically you need to calculate vorticity. You plot the vorticity, you see this.
Okay.
Yeah, that's also in this picture here, and in this equation 21 here, I suppose you can compute this equation, the location and the time, if you do numerically. I didn't do it. I don't know how to do it, but I think that's possible. Yeah.
Okay. Thank you.
Other questions, comments?
Yeah.
So I have a comment at the beginning. You discussed the cosinus equations, and everyone should hear soon. And you show something that looks like an energy, but actually it's the sum of a kinetic energy and a rate of entropy production. So
you could think that way, yeah. You could think one way, but it's the energy related to how the temperature this like in non-homogeneity of the temperature, right?
Yeah.
In the region.
So it's not an energy; it's a rate of entropy production. The second term. I don't see how.
But
this
it is type of energy because. This K and some constant, there was some coupling constant there, and everything will be in unit of energy. Yeah. Mm-hmm.
Okay.
Yeah.
So you have to impose a time scale somewhere. I mean.
Yeah, the time scales. You see. Yeah, you're right. You're right. In different models have different time scales. Here, like A, some relaxation. Sometimes it's a relaxation time. Sometimes it's a real time. Yeah, depends on the system you're talking about. Yeah, you're right.
And also, I don't see, you don't have a potential energy in this case. Usually you have gravitational potential energy in a Boost-Nash system.
Here, we put it in the B here. We put it in the B here. If you say, okay, yeah. if you forget just the Navier-Stokes, you forget about temperature, and then you could have those things included too. Yeah. But it's just a formula. One of the reasons we wrote down this is that to give you some guidance. When you build a model, and this is very explicit, especially in a system where, like, for interactions, for instance, for four fundamental forces. For the forces, you have n standard action, you have Yang-Mills, standard Yang-Mills, nothing else. And for electromagnetism, you have this Maxwell thing. It's unique. And so with this type of energy, you derive the law. So that the reason I'm presenting this is that you have some kind of guidance. If you break this type of thing, something may go wrong. It doesn't mean that the model is incorrect. You may get a good approximation. Yeah, but this may give you some kind of guidance. And at least so far, we found 9 exceptions. Most can be everything we encountered of this type. Yeah.
Right. I propose that we thank our speaker once more.
Thank you.